Hello everybody, my name is Param Damle and welcome back to my series on quantum machine learning. So if you haven't seen the first installment of the series, I would highly encourage you to do so because a lot of what we're going to be talking about today regarding quantum circuits is going to be a continuation off of last time. Just a reminder, this is a series of lecture videos about a course that I taught at the University of Virginia in the spring of 2024. I'm bringing it to you online today so I can expand my love of quantum, my love of machine learning to the greater YouTube populace. So let's just jump into it. So doing a little bit of recap of last week, what are some of the properties that we talked about that would be highly important in this course in terms of what differentiates quantum computing from classical computing? Well, first we have superposition, right? The idea that these bits are not just 0 or 1, like in classical computing, but that they can be some proportion of 0 and 1 at the same time. Another important quality is quantum entanglement. Now this was the idea that sometimes quantum states can't be broken up into independent probability distributions. For example, if we have the state 1 over square root 2 times ket 0, 1 plus 1 over square root 2 times ket 1, 0, that can't be broken up into a 50-50 probability of ket 0 or ket 1 on the first qubit and ket 0 or ket 1 on the second qubit because those probabilities really depend on the values of both qubits at once. But what really exactly is a qubit, right? We said that a qubit was basically a wire in our quantum circuit, and it can be written as some multiplier of ket 0 plus some multiplier of ket 1, where the squared norms of both values have to add up to 1. We mentioned this is because a qubit should act as a probability distribution. You have some probability of measuring 0 and some probability of measuring 1 on any given qubit. Now, if a qubit is just ket 0, then you pretty much have a 100% probability of measuring ket 0, so that would be written as alpha equals 1 and beta equals 0. We use ket notation to simplify the way that we're writing these qubits as vectors because as the number of qubits grows, the quantum state, the size of the vector increases exponentially. So in order to avoid writing exponentially sized vectors, we use ket notation. For example, if the bit string inside the ket is 0, 1, 1, 0, it's a column vector with 4 bits, that's 2 to the 4, 16 zeros, except at position 0, 1, 1, 0, which is index 6, and if we're using 0 indexing, that's the 7th position down, that will have a 1, and everything else will have a 0. So this is the notation we're going to be using extensively moving forward in the course, and it's assumed that you should have a good understanding of what this means, and if you don't, feel free to leave a comment or seek other resources about ket notation, about quantum computing, and it's a fairly well understood concept. Next up, what is a quantum state, right? So we talk about individual qubits, but we also mention this concept of entanglement, where if you have multiple qubits, they can get entangled into one larger quantum state of all the wires in consensus. So a quantum state, just like I said, is a combination of multiple qubits, right? You can have independent states where different qubits can just be multiplied together to get the overall quantum state, right? So in this case, if the first and third qubit are always ket 0 and ket 1 respectively, and the probability of the second qubit being ket 0 or ket 1 doesn't depend on the other two, then we can just write it in the separated form with the 3 kets in order, or we can multiply them across and just write them in combined order like so. The quantum state, the different states that make up the quantum state can also be dependent, right? So the different qubits can be dependent on each other, can be entangled, and in this case, the probability of the first or third qubit being 0 or 1 absolutely depends on the middle qubit, right? If you know that the middle qubit is 0, you know for a fact that you're going to measure the first qubit to be 1 and the third qubit to be 0, right? Just like with qubits, we also want the different norms in this quantum state when they're squared and added up to equal to 1. And that's because just like with regular qubits, the squared norms in this instance are going to represent the probability that when we do our measurement on our circuit, we're going to measure that 0 or 1 value, right? So we're going to get to this later, but these quantum states are probability distributions, but that's the probability of measuring a particular set of values across all of the wires in a quantum state. What operations can we apply to these quantum states, right? We talked a bit about the types of ways we want to transform this probability distribution, and we said that the quantum gates we want to apply are like square matrices that take in a column ket vector and then output a column ket vector. That's also a valid quantum state, right? So an important thing is that these matrix operations are unitary. We're taking a vector whose squared norms add up to 1 that represents a probability distribution, and we're outputting a vector whose squared norms add up to 1 and that represents a probability distribution. Because we want to make sure that we're taking in a valid quantum state and we're outputting a valid quantum state. So we've talked a lot about the theoretical and mathematical side of it. What does this actually mean in practice, right? I'm not going to get into this too deeply. Like I said, this course is meant to be more from a math and CS perspective as opposed to a physics perspective. But if we're talking about the actual implementation, we have multiple layers that go into an actual physical quantum process, right? So at the very top, you have programmers like you and me, right? You have classical infrastructure, classical computers that people program, write quantum instructions in, and send these instructions via a console to whatever quantum setup a given company or research lab may have, right? Inside the actual quantum setup, you have these qubits, which are often represented in terms of charge or spin, some other quantum plus or minus property that we can study. And a common implementation are electron pairs in a Josephson junction, which is basically separated superconductors that have the electrons move and spin in a particular way to either produce a measurement of 0 or 1 on that qubit wire. You have a converter for these inputs from a classical computer. This programmer saying, hey, this is the quantum circuit that I want to build. You have a converter from that onto actual quantum signals, right? Do we perturb the charge? Do we perturb the way the current's flowing in our given setup? And at the very end, you have some sort of qubit storage unit, right? You want some way to physically put these electrons or other particles in a controlled environment that is not going to be affected by the heat and the electricity out in the greater environment, because that can really impact your experiments and add confounding variables, and we don't want that. The reason that we don't want confounding variables is that even with slight perturbations, the entire quantum setup is very prone to decoherence. Any slight change in temperature, energy, anything like that can cause many errors. And right now, modern contemporary quantum systems are highly prone to errors. So for every one logical qubit, or the kind of qubits we're going to talk about, these theoretical ideas of wires in our quantum circuit that behave a certain way, in practice we're going to need a lot more physical qubits, just because so many of them are going to end up being tampered with or faulty or have a high error rate. Because of this, many quantum scientists consider us to be in the NISQ era. That means that the quantum computing that we're engaging in is noisy. There's a lot of additional noise on the measurements. We can't get a clean measurement of anything. Intermediate scale, which means we're not starting out at the foundational level, but we're nowhere near scalability yet. We're nowhere near cracking major crypto algorithms or running major quantum circuits. We're in more research lab settings, education settings, building out the technology more. If you are interested, Wikipedia has a great article about the different physical implementations of qubits. There's so many different options, and what we're going to be talking about in this class is primarily the theoretical idea of a qubit that hopefully could be generalized to the most practical use case among these shown here. So let's talk a little bit about how you can expect to solve problems in this class and in your quantum career in general, right? Obviously, you're going to need to start out with a problem. You don't want to tailor a problem to a solution. You want to tailor your solution to an existing problem, right? Usually in the realm of quantum computing, this is either a certain type of computation, algorithm, or expensive workload for a computer that can be highly parallelized with a quantum computer. Next, you may want to devise a quantum algorithm that uses some arrangement of the circuit, some properties of linear algebra that we're going to discuss later that solves this problem, right? We're going to need some way to initialize some inputs, run this algorithm or circuit you've created, and then measure the outputs to get the solution to the problem. Now, once you have the idea and the math laid out, you need to actually physically consider what is a quantum circuit, what gates are we going to use, what signals are we going to send to which qubits in order to transform our desired input into our desired output. A quantum compiler, such as one provided by a company like IBM, will compile these intentions into actual physical gates, actual lasers being shot at quantum hardware or additions of energy or charge or spin that will try to execute this circuit as closely to your intentions as possible. And lastly, once all the planning is done, there's the actual execution and implementation, either on a quantum processing unit or QPU, which is the physical quantum hardware we talked about earlier, or more reasonably in some sort of classical simulation software, so you don't need to run expensive quantum trials and you can quickly iterate by testing your solution on a simulated quantum setup and see if it works first. Let's take a look at what our quantum circuits look like, right? As you can see in the diagram, it kind of looks similar to a classical circuit you may be familiar with these wires that each represent a different bit, and you have some operations that you're doing on each wire, right? So the wires that start with the letter Q are qubits, right? They have superposition entanglement. The entire set of qubits in a circuit represents their shared quantum state. At the bottom with C, you have 3 classical bits. These are the bits that you know and love that can either be 0 or 1, but not both. And the idea is that we're going to take these qubits, we're going to apply some gates on them, and those gates you see there are all unitary matrices. So imagine that the quantum state is represented by a big ket vector. We're applying all these matrices by multiplying them. And then at the very end, once we've transformed our quantum state, we're going to measure, right? We're going to sample the distribution, and we're going to get a concrete set of zeros and ones for all the qubits. And these are going to get measured onto the classical bits, which are essentially going to store the value so that we can read it. An important thing to note, in this class at least, is that we're going to treat the top wire as the most significant qubit. So the top wire is going to be Q3, which is going to be the leftmost value in our ket notation, so our leftmost bit, and the rightmost bit in our ket notation is going to be that bottom value. So what are these gates in the circuit actually doing, right? We talk about how in general our quantum state is going to be like some kind of distribution, right? So something like this, right? And if we want to ensure that we have some destructive interference here, some destructive interference here, and we want to boost the probability here because this is the value associated with the output we want to measure at the very end, right? Essentially, our gates are going to perform constructive and destructive interference to sort of mold the distribution to be more like what we want it to be, so that when we measure it, we can get an answer that we like better. So it's really that simple, right? We treat quantum states as probability distributions. We change the distribution to how we want it to be in our answer, and then we repeatedly measure to try to get the answer we want, right? So imagine if of these 3 humps in the probability distribution, I knew that some series of gates would accentuate the peak that corresponded to the answer to one of my problems. Then I would run the simulation a bunch of times, keep measuring the answer, and whichever answer appeared most often, well, it's a good chance that that's going to be the answer to my problem. Do note that a lot of circuits we're going to talk about in this class have ancillary or helper qubits. As you can see, Q0 here is never measured, so we never get its actual value, but it has some operations that it shares with other qubits, and so all of these qubits still exist in a shared quantum state. So if they're entangled, remember the probability distribution of one affects another. So if we affect Q0, we're going to be affecting Q1, Q2, and Q3, and we're implicitly going to be measuring Q1, Q2, Q3, and that's going to tell us a lot of information about Q0, even if we don't necessarily care to measure Q0 itself. Moving on to the quantum gates. We said before that quantum gates are represented as unitary matrices, but what does that mean in the context of a circuit? Well, the state in our circuit is represented as a column vector. So when we imagine applying a gate, we're effectively just multiplying this unitary square matrix from the left against our column vector, which we can represent in general as ket psi. The actual implementations for unitary matrices or for quantum gates involve interactions with the environment, but we're going to pretend to ignore those to simplify the setup for this class. especially as we get into more complicated topics like machine learning. So as you saw in the circuit diagram earlier, these gates are going to be applied upon certain qubits. It can affect a single qubit, it can affect a range of qubits. Even affecting a single qubit could impact the distribution for a different qubit if these two are entangled, right? When it comes to matrices, we can always consider the identity matrix, which replicates its input into its output, as a no-op, or no operation, the same as not applying a gate at all. So every single operation, even if it works on some qubits, can be considered to be applying the identity matrix to the qubits that nothing is changing for. A pretty important result in quantum computing is the Solovay-Kitaev theorem, and what this basically tells us is that this representation of gates is kind of universal. That means any type of operation we want to do on a quantum state can be represented as some unitary matrix. And so, because these matrices are so fundamental, people have put in a lot of work into deriving a set of fundamental building blocks. And the theorem states that once you have these building blocks, any possible gate can be created using some combination of these building blocks. And so regardless of how quantum computing advances, at the very end, we will still be doing operations that are some different arrangement of these fundamental building blocks that I'm about to show you now. So the first building block we're going to look at are Pauli gates. They're named after the letters X, Y, and Z, and they all sort of represent different dimensions that a unitary gate can go in. And when you have an actual gate that you're applying to a quantum state, it can be seen as some point at each of these Pauli gates that combine into a composite gate that you're applying to your circuit. The first gate is the X gate, the sigma X gate, or the NOT gate. Often represented by this XOR symbol, the circle with the plus through it, it basically turns ket 0 into ket 1 or ket 1 into ket 0. And the reason that it's represented by an XOR symbol is that you can consider applying this gate to some ket A as 1 XOR that A. So if A is 0, 1 XOR 0 is 1, and if A is 1, 1 XOR 1 is 0. An important thing to note is that unlike in classical computing, this NOT operation is not operating on the values in the vector, but in the index, the value inside the ket notation, right? So when we're flipping values inside a ket, we're essentially moving these probabilities around in the distribution instead of flipping the probability itself, or the phase of the probability. Now the sigma Y gate, I don't really know how to explain it, it's just that. It's not very special and it doesn't have a clear name to it, but the sigma Z gate is a lot more well known, the phase flip gate, right? This one does nothing to ket 0. Ket 0 passes through unchanged, but ket 1, its amplitude is flipped, right? So if you go in with alpha ket 0 plus beta ket 1, you're going to leave with alpha ket 0 minus beta ket 1. And so this can be considered as you're raising negative 1 to the power of A, and you're multiplying it by A. Now those gates would not be complete without the crucial addition of the Hadamard gate. So the Hadamard gate we're going to be using extensively in this course. This gate, it's a little tricky to explain, but an easy way to think about it is that 0 will be turned into equal parts ket 0 plus ket 1, and ket 1 will be turned into equal parts ket 0 minus ket 1. So you obviously have to add a 1 over square root of 2 amplitude there to make sure that all the squared norms add up to 1. Another way to represent the Hadamard is 1 over root 2 ket 0 plus negative 1 to the A ket 1. So if A is 0, that'll be a plus ket 1, and if A is 1, that'll be a minus ket 1. One of the reasons that the Hadamard is very powerful and used widely is that it's also its own inverse. So let's take a couple moments to see if we can prove that the H gate is its own inverse. So one way we can do it is using standard matrix multiplication, right? If we multiply H with itself, row times column wise, do we get the identity matrix back? And if we get the identity matrix back, what that means is that if we apply H twice to the same column vector, that's the same as applying the identity matrix to the column vector, and so it's equivalent to doing nothing. Next up, we can also verify that H leaves an input state unchanged by seeing what it does to a general qubit. So we said before that we can represent any qubit as alpha ket 0 plus beta ket 1. And so if we apply h to this, what happens? I'm going to sort of speed through the derivation here, but what you can see is that we're essentially foiling and splitting over the matrix multiplication into multiple terms, then conjoining them all, and at the very end, we see that we still get alpha ket 0 plus beta ket 1 out, the same input that we put in. These are just two of the tools we can use in the future, especially in this class when we're proving mathematical properties or deriving solutions for problems. We can treat things in a purely matrix sense, we can use primarily ket and bracket notation, or we can use other general higher level representations that we're going to get to later in the course. So far, the gates we've talked about have operated on single qubits independently. What if we use certain qubits to affect others, right? With controlled gates, what we're saying is that if the control wire, the first wire, is ket 1, then we're going to apply a gate to the second wire, regardless of the second wire's output or value. And if the first wire is ket 0, the second wire is going to pass through. It's just going to have an identity operation. So one example is a controlled NOT. So in case ket 00 or ket 01 pass through the controlled NOT, since the first bit inside the ket is 0, nothing is going to happen to those values. However, if we pass in ket 10, that second value is going to have a NOT gate applied to it. So it's going to become ket 11. And if we pass in ket 11, because the first bit is 1, it's going to activate the control, and that second bit is going to be flipped, so we get ket 10 back. If you are more of a visual learner, you like seeing the matrix representation itself, you can see that in this matrix, if the first bit is 0, the value is going to be up here, and it's effectively an identity. But if the first bit is 1, this gate is going to get multiplied by the second bit, and so the value will flip from 0 to 1 or 1 to 0. Another layer on top of this is we're going to add a Toffoli gate, which is a controlled NOT. And so what this means is that we're only applying a NOT on that third bit if both of the first two wires are 1. So if the first two values are 00, 10, 01, nothing's going to happen. But if the first two values are 1, 1, that third value, that C, is going to get flipped into from 0 to 1 or 1 to 0. And you can see, just like in our controlled NOT gate, if the first two bits are 0, it looks like an identity matrix. And if both of the first two bits are 1, then that little 2 by 2 is going to get multiplied with the third bit to flip its ket value. Now, keen observers may see that there's a bit of a composition at work here, right? Like, we can see how this is just a bunch of 2 by 2 identity matrices composed together, and how this is a X gate or a NOT gate composed into the very bottom right corner. And you're absolutely right that this does mean something. Now, this represents that the operations are independent and do not affect composite states, right? So if we want to perform different operations on separate qubits, then the representation we use is a tensor product or Kronecker product. And it's represented by this O with an X through it. And what it's basically saying is that if we're applying A on the first qubit and B on the second qubit, the overall gate we're applying to this bigger state is just A tensor product with B. And what that means is that take this entire matrix of B and move it, multiply it by each one of these values. So you can see how B is being multiplied by all the values in A. It's as if it's being composed inside each value of A. And so what happens is, for any first qubit, right, a value within A is selected to multiply by. And within that, the values of B are multiplied with the second qubit. So a more expanded form of this matrix is given here. You can see how all the individual values, it's literally like we're just positioning the matrix B at several different points in this bigger grid. A more colorful representation I came up with is that if we're tensor and producting this like grayscale gradient with the colors red, blue, green, and yellow, what you can see is that the outer shape retains that first matrices red, blue, green, and yellow, but within each subsection we have this gradient shape that's taken over. So speaking of these tensor products, what if we applied this Hadamard gate, this H gate that we have learned about, to each of n qubits if we have n wires in our quantum circuit? right? So let's say our quantum state right now is ket x, right? Where x is a bit string and each of these values x0 through xn, there's n qubits, each of them is either 0 or 1, right? What we want to say when we apply a h tensor n in this way is that we're independently applying h to each qubit in our greater state. So what does this mean? Well, a formula that you probably don't have to read too deep into is that when we have an n-tensor Hadamard, the matrix can be represented as, for all possible bit strings of length n, you have the summation of this term here. And what does that mean? Well, if we multiply each tensor n with ket x, right, we simply carry over the same formula we had, but then we join a ket x. And we notice that once we join a ket x, this forms a nice little inner product for us. And so what we say is, well, z inner product with x, we learned that that produces 0 when the values are orthogonal. And when it comes to kets, when are they orthogonal? Well, it's when the bit string is different at all. Because remember, the bit string inside a ket represents the index of the only one in that entire vector. And so if the indexes are different, those ones are not going to line up, and the inner product is going to be 0. So instead of this summation over z, we can get rid of all the terms where z does not equal x, right? Because the only time this is going to be 1, or the only time it's going to be non-zero, is when z equals x. So we simply replace z with x, get rid of the summation, and this is the value for applying an n-tensor Hadamard on a n-bit quantum state x. Let's do some quick exercises to verify our learning. So for the first one, let's see if we can write out this complex matrix vector multiplication using ket notation, right? So one thing that screams out to me right away is that we could just represent the matrix we have here in terms of its row vectors as in bra notation. What we can see is that we can also expand the h times ket 1 into 1 over square root of 2 times ket 0 minus ket 1, and that we can distribute using FOIL the ket 0 and make sure that because we're multiplying from the left, that ket 0, that 0 bit, goes on the left of all the bits to its right. So it'll become 1 over square root of 2 times ket 0, 0 minus ket 0, 1. From there, it's regular linear algebra, matrix times column vector multiplication, but this time we can use a key property that the bras with a different index do not multiply with anything on the right in terms of kets because the ones won't align. So we only have to consider the inner product when the index inside the bra and the index inside the ket is the same, because that's when the inner product will be 1. Otherwise, the inner product will be 0. And really quickly at the end, we just want to verify both that the squared norms of our resultant vector add up to 1, making sure it's a valid quantum state. But also, we want to write out our solution in kets like the problem desires us to. Alright, and lastly, we've been considering a lot of tensor products, Kronecker products, independent operations, and is this matrix a separable operation? And if so, what is it a tensor product of? Now, a lot of you may already notice the general shape of zeros in the top left and bottom right corners, and we have 1 values because the bottom left and top right are roughly equivalent in magnitude. Now, within these quadrants, we can see that there's a general common factor of 1 over square root of 2 that we can pull out. Top left 3 values tend to be the same sign where the bottom right value is a different sign, so we can pull that out. And this is what we get as the tensor product that produces this matrix. And what you might notice is that the right matrix of the two is actually the Hadamard gate. And with that, that's all I have for this class. Make sure to let me know any questions, comments, or concerns about the lesson today, and stay tuned for the next installment in the series in which we're going to get a little more serious with quantum algorithms using some of the tools that we've learned today regarding how we can represent circuits and operations upon them. Thanks for watching, and I'll see you next time. Bye.